Wait for a few more folks. We're going to wait just about another minute before we get started. We have this joke about Lamont time, which is we never really get started until 5 minutes after the announced time. Never been able to change that. Okay, we're building rapidly. Just another few seconds. Okay, we'll go ahead and get started now. Well, welcome everyone. I'm Lerner-Lam. I'm a retired member of the research staff of Lamont-Doherty, and I want to welcome you once again to our Earth observations and conversations with our Lamont crew. I'm at home looking out the window with snow falling down. We have had an early winter so far. We are in meteorological winter, but it is early, and I've got about a foot and a half of snow on the ground, which must mean, according to some of our folks in government, that global warming is over. But it's not. And we're going to hear today from some of our folks who have worked in the poles, particularly on the ice, to understand a little bit about what the climate is doing to the ice caps, the ice sheets, and the ways in which those interact with the rest of the planet as well. So today we're happy to be joined by Sidney Hemming, who is a professor in the Department of Earth and Environmental Sciences and in the Geochemistry Division at Lamont, and Brendan O'Reilly, who is in our Biology and Paleoenvironment Division within Lamont, both of whom have been working for many years around the globe, but particularly in the polar regions. We'll be starting with Brendan. I'm going to ask you to put your questions into the Q&A tab. We'll be monitoring that. We'll also monitor the chat, but the Q&A is easier for us to be looking at. Since this is a webinar, Q&A will be the main way in which we'll interact with you. So we'll get the lightning talks from Brendan and then Sid, and then we'll have some moderated Q&A after that. Okay, Brendan, your turn. You're up.
Well, thanks, Art. Let's see. Okay, so as Art mentioned, my name is Brendan Reilly. Since coming to Lamont about 3 years ago, I've served as the director of the Lamont-Doherty Core Repository, and I'm sure if many of you have visited the campus before, maybe you got to see our facility. And I also run the Lamont-Doherty Paleomagnetics Lab, which I'll talk a little bit more as we move forward. A lot of my work is thinking about Earth history in the polar regions. And for this talk, I'm going to highlight some work that we started in 2023 in Baffin Bay, a field season that we did there. And before we get up to the Northern Hemisphere, I wanted to start by thinking about, why we care about past ice sheet changes. And one of the reasons is that ice shelves are important for the stability of Antarctica. And so ice shelves are the floating extension of grounded ice, and they're important for the stability of the ice sheet because they act as buttresses, and so they slow the flow of the glaciers going into the ocean. If we're going to predict how Antarctica will change in the future and its contribution to sea level rise, it's important to understand the physics and dynamics of these ice shelf systems. And I think that's been highlighted in some interesting recent work that shows that even in high emission scenarios, there's still a great deal of uncertainty of how some of these really large ice shelf systems in Antarctica will respond to the future climate change. And so here I'm just zooming in on this ice shelf here, the Filchner ice shelf, which is in the Weddell Sea embayment. And so this is the floating portion of the ice shelf. Here's the grounding line. And these ice shelves are fed by these fast flowing ice streams, and they act as a stabilizing mechanism or buttress to those ice streams. The ice shells themselves can be sensitive to atmospheric melting from above or oceanographic melting from below. But if we really want to know what happens when one of these big ice shelves leaves the planet, there's really not a whole way of knowing because we haven't seen an ice shelf of this scale actually break apart. And so we'd have to study it either by modeling the systems or by going into the past and observing actual examples of ice shelf breakup in the past. And so in terms of thinking about the geologic record, I really like this comparison of if you take this ice sheet and you remove all the ice from it and look at what the topography looks like underneath, you would see something that looks like this. It's an island archipelago. And where these big ice streams that feed the ice shelf existed, there are these channels, say famously like the Recovery Glacier. And so these glacial systems are really powerful erosive agents, and they shape the landscapes around them. And those landscapes and the sediments that accumulate at the ice margins can be used to understand the history of the systems. And so as a geologist, if this is a landscape that I want to understand today, I can look to see where on Earth do we see something similar to that. And a really beautiful example is up in the Northern Hemisphere in Arctic Canada and around Baffin Bay, where you have the Canadian archipelago with these channels where these former ice streams used to live. And so if we wanted to study really dramatic retreat of ice, I think that this is a really good place to go and take a look at it. And so that's what we did in 2023 on the ship, the RV Neil Armstrong. And so this was a project that I led with Shannon Klotzko at UNCW and Rob Hatfield at the University of Florida. And we investigated a number of things. The part that I was the most involved with was the sediment coring and using those sediments to understand paleo environment. But there was also work in terms of looking at the modern environment to think about or calibrate the way we think about the past, mapping the seafloor, and then training the next generation of Earth scientists. The places that we were most interested in targeting were the places that we think were most likely to preserve the imprint of the past ice sheet or had their landscapes, shaped by those ice sheets. And so this was exactly the sort of thing that we were looking for. And so we were looking for these transitions between where we see the seafloor being carved and shaped by those ice sheets and where they weren't. So we call this the ice contact boundary, and we're interpreting these boundaries as the maximum ice extent at the last glacial maximum or in the last ice age. And so this image here is from northern Baffin Bay, and the environment would look something like this with an ice sheet that extended onto the continental shelf and then terminated as a floating ice shelf. And so work that's being led by the geophysics lead on the project, Shannon Klotzko, has gone all the way around Baffin Bay and used the data that we collected as well as existing data to map where's the deepest point that we can see these ice contact features or these ice contact boundaries. And from that, we've been able to define the size, the geometry, the extent of this large ice shelf system that's sat in this area. The takeaway is it was a really big ice shelf. It was really thick, and it was fed mostly by these northern ice streams, particularly this one here, the Boothia-Lancaster ice stream, which came out of Arctic Canada. And so the work that we're doing here at Lamont-Doherty is taking sediment cores that are from around these ice contact boundaries to start thinking about what were some of the causes of these initial instability from the last ice age or the last glacial maximum? What caused the ice shelf to break up? How fast did those ice streams retreat? And what were some of the dynamics of the ice retreat? And this is I think it's an exciting thing to be a part of. Most of the work that's been done so far up in this margin has focused on places that you can access on land or on the continental shelf. And so this is really an unexplored area, thinking about what the environment was like, say in this setting when the ice was at its maximum extent and what caused that retreat. And to do that, so we're using these sediment cores, and from the sediment cores themselves, we can infer some glacial processes that are happening. And so here I'm just showing you an example of an interval in the core where we see a big transition. Below this transition, the lithology or the sediments tell us that meltwater was really important. So the ice was losing a lot of its mass by melting. Above that transition, we see coarser particles that were related to transport of particles by icebergs, which I think you're going to hear a lot more about in Sid Hemming's lightning talk coming up next. And so that tells us that there was a different mechanism of mass loss at that time of icebergs calving off the front of the glaciers. But as you can imagine, these sub-ice shelf environments are quite challenging to work on. And a lot of the proxies that we typically use in paleoceanography aren't available for us to use in this setting. And so I just wanted to highlight some work that's being done by a talented postdoc here at Lamont, who has been thinking about proxies that we can use in this environment that tell us something about what the environment is like on in front of the ice shelf, then also thinking about ways of tracking advection or how much water is moving beneath the ice shelf cavity itself. The other challenge that we're having is thinking about how to date these systems. And so because nothing is living under the ice shelf, we don't have any material to radiocarbon date. And so to assess this or to address this problem, we've been utilizing one of the new capabilities in the Lamont Paleomagnetics Lab. This is a newly installed instrument. It's called the Superconducting Rock Magnetometer, and it's optimized for working with sediment core samples. And using this instrument, we can reconstruct how the sediments record past variations in the Earth's magnetic field that are at the same stratigraphic horizons as the glacial signals that we're interested in. And so using cores from up in northern Baffin Bay, we've started to reconstruct how the Earth's magnetic field has changed back through time. And we can take this signal and then compare it to signals from further south in the more open ocean, in which we can get radiocarbon and independent-based age models, and use that to start thinking about the timing of things like the IRD events and the rates at which these glacial changes are happening. And so with that, I'll just end with, we're just really starting to explore these archives, but I think it's a really exciting area of research. And I'm also really excited for the work that we're doing here at Lamont, developing some novel methods to tell time and to understand these paleo environments. And in doing so, we can use these ancient systems to think about ice shelf processes, mechanisms of retreat, and the timescales associated with all of that. So thank you very much.
Thanks for that, Brendan. By the way, I think I introduced you as O'Reilly, not Riley. Sorry for that. Pardon my own bias here, I suppose. Anyway, please let me remind you to put your questions into the Q&A tab. That's the easiest one for us to monitor in this webinar format. Okay, let's turn it over to Sid, who will be amplifying some of the work, and then we'll go to the Q&A. Okay, Sidney.
Am I showing up?
Yep, there you are. Mm-hmm.
Okay. Thank you. So what if I were to tell you that large portions of Antarctic ice sheets could fall into the ocean due to global warming? We don't really expect that to happen, but this low likelihood, high impact storyline includes ice sheet instability processes that we do not perfectly understand, they're starting to include proxies for this into numerical models, but there's still a lot more to be understood about that. And our historical records are too short to document the full range of potential instabilities. So we must rely on geological observations that must be also supported by numerical simulations in order to probe the behaviors of the ice sheet. So this is just a series of maps kind of setting the stage for Antarctica. The map on the top, the yellow is the parts of Antarctica where the topography is below sea level under the ice. The blue parts are the ice shelves, like Brendan was talking about in the previous lightning talk. and some of the place names around here. On the bottom left, the blue colors are the same as the yellow on the top, and they represent the range of depths below sea level. And then on the right-hand bottom is the thickness of the ice above the flotation, where it's below sea level. And West Antarctic ice sheet has a lot of its surface base below sea level. And the West Antarctic ice sheet contains enough ice to raise sea level by about 4.3 meters. The ice is about 1 to 2 kilometers thick, and it's mostly grounded below sea level, whereas the East Antarctic ice sheet contains far more ice, enough to raise sea level by about 53.3 meters. The ice is generally about 3 to 4 kilometers thick, but it's mostly grounded above sea level as you can see in the gray area here. So what we're doing for geological evidence is using ice-rafted detritus, as Brendan alluded to in the previous talk. And this cartoon on the left is meant to kind of give a little bit of a demonstration of how we're thinking about this. So different aspects of the geology are recorded by the sediment particles that are derived from the ice and dropped into the ocean. And so the different colors on this cartoon indicate different geological features, and the grains in the bottom of the icebergs melt out and get deposited into the sediment. We also get things like the subglacial meltwater, like Brendan mentioned in the previous talk. I'm going to be really focusing my attention on some sites that from an expedition, Expedition 382 for the IODP that Brendan and I actually met on, both sailed on that expedition. And I'm going to be talking about a time interval that's similar to the one that Brendan was referring to in Baffin Island from site U-1537 in what's called Iceberg Alley. And this is the northern tip of the Antarctic Peninsula and the southern tip of South America for geographic reference. So the reason that we can use Argonne geochronology, which is the tool that I use to help trace the sediment sources, is because there's a lot of variation in the geology around Antarctica, in the geological ages of the rocks around Antarctica. And the diagram on the right is a series of pie charts. The time scale legend is shown on the bottom right of this diagram. And what you can basically, don't worry too much about the geology unless you want to, but what you can see is that the ages range widely around the perimeter of Antarctica. And that's a really big advantage for us because we can date detrital grains and therefore make inferences about where they must have derived, where the icebergs must have calved off the margin of Antarctica. And on the right-hand side is an animation of the observed very large icebergs coming from Antarctica since the 1970s. And hopefully you noticed it while I should have probably talked about that one first. In the end, the color around the perimeter represents where the icebergs came from, and the color spots that you see remaining on the map is the last place the iceberg was seen, tagged to where it came from on the continent. So these are large icebergs that came from ice shelves and probably didn't have much, if any, ice-rafted detritus in them, but these colors represent where they would have flowed around the continent and ended up. And in the case they did have ice-rafted detritus, we would see sediments of those ages coming from that sediment core. So another animation that I want to show, this is a close-up of the sort of geological age variability that we've documented around the proximity of the Iceberg Alley sites. And the animation on the left is a numerical simulation that is based on geological evidence going from 25,000 years ago to the present. And the color bar on the bottom is the velocity of the ice, with red bright colors being the rapidly flowing ice, and the dark colors being slower ice, and the very dark color is the ice divide. So ice, like rivers, flows downhill from divides, and so all the ice on one side of the divide flows opposite direction. And what you can see is that the distribution of the rapid flowing ice is not even around Antarctica, and these ice streams, like some of the ones that Brendan referred to from both the Weddell Sea area and also from Baffin Bay, are the places where major movement of the ice from the continent into the ocean is happening. So what we wanted to do was to really examine that interval between the transition from the last glacial period to the Holocene in Iceberg Alley from site U1537. And so what's shown here is on the middle diagram, the purple is the magnetic susceptibility measured on the sediment cores, and that's a proxy for the environmental conditions. So the glacial time has high magnetic susceptibility going to the left, and the interglacial time has lower magnetic susceptibility. And the black curve here is the ice rafted detritus abundance counted as grains greater than a millimeter per centimeter of sediment. And you can see that there's three prominent peaks in ice rafted abundance across this interval. So looking at the sediment provenance, these pie diagrams are like the ones I've been showing, and then we've also plotted these data as histograms. What we can see here is that during the last glacial maximum between 25 and 21,000 years ago, there's a relatively low abundance of ice rafted detritus. And if we look at the pie charts, we can see a lot of green, orange, and red representing a variety of East Antarctic sources. In the three peaks, we also see those same colors, plus we see a lot of the sort of lighter pink colors, which is the West Antarctic contribution, and then and of course high abundances. And then in the Holocene, we see again lower abundances of ice rafted detritus, and we see much more dominant West Antarctic sources in the pie charts. So our current understanding of how the ice shelves work, and they'll be elucidated by the work such as what Brendan was describing, is that the timing of iceberg peaks and Iceberg Alley coincide with changes in the ice shelves, whether they're advancing or retreating. Because when the ice shelves are fully extended, the icebergs that do calve off are clean of sediment because there tends to be a melting process at the bottom of the ice shelf that removes the sediment. And so when the ice shelf retreats to the grounding line, then the ice streams are bringing dirty ice into the ocean, and we see ice rafted detritus. Conversely, if the ice streams retreat far enough inland, they aren't going to be calving into the ocean, and so we won't have ice rafted detritus. And so therefore, we think that the IRD peaks that we see represent transitions in the state of the ice sheet. So for future work, we now have a small grant from the Comer Global Climate Change Foundation to basically double the number of measurements across that interval that we just looked at. And our data is going to be integrated with ongoing data from the other Expedition 382 scientists to better understand the context of the IRD changing with other environmental factors. The magnetic susceptibility and other shipboard data are really important environmental indicators, but the additional shore-based work is going to greatly refine our understanding of the environments. And we're also working on other intervals through the site. We have a beautiful record going back to 3.3 million years. So this work is building towards a vision of a comprehensive understanding of how ice sheets respond to climate change. So to sort of end with a vision, decades of drilling and environmental proxy development have led to an extraordinary understanding of the history of Antarctica's ice sheets. But with all of that, we still don't know enough about it. And the paleoclimate and cryosphere communities, and especially Lamont, are poised to make major breakthroughs in our understanding by combining geological observations, modern observations of the ice margin and surrounding oceans, and numerical simulations of past ocean currents, winds, ocean temperature, and associated ice street responses. And it's really critical to maintain momentum in this quest for better understanding the ice sheets. Thank you.
Oh, thanks, Sid. Again, please put your questions into the Q&A, and we'll turn to that in a minute as those questions build up. But I want to start the conversation with Brendan and Sid a little bit about this momentum issue that you're talking about. Not just the momentum in the science, but the momentum in the facilities as well. And I see on the participant list a lot of friends and colleagues and alum from Lamont as well. And they all, I think you all know about the core lab at Vermont. Brendan, you're now the director of the core lab. Why don't you give us a 2 minute sense of the history of Lamont's Core Lab and its importance to what you're doing and what Sid's doing?
Sure. I imagine a lot of people here have been to the Core Lab, but as a brief overview, today the Core Lab operates as an NSF-funded facility that serves the larger marine geology community. We have over 20,000 marine sediment cores from throughout the world's oceans, in addition to rocks and corals and other types of geologic samples. The collection was started back in the late 1940s when, during a cruise of opportunity, some sediment cores were taken from the Atlantis, and it was quickly realized how interesting these cores were. And then, following the formation of Lamont and the acquisition of Lamont's first ship, Vima, there was a program to sort of more systematically explore the ocean and collect sediment cores every day, no matter where the Lamont ships were. And so that started to build the collection. The thing that I like to bring up that I think is really interesting is if you look at our statistics on the rate at which cores came into our collection and the rate at which samples went out of our collection, these early cores from the Vima and Conrad primarily came in the 50s and 60s and early 70s. The majority of the samples that went out of the repository, there was a huge spike in the early 70s around the time that this program CliMap was started. And I think it's a really good example that these facilities are important. And sometimes we don't always envision all the science that's going to come out of this work until after there's been some time for the fields to mature and for us to learn more about what we're working on.
I think that's an important point, Brendan. And in fact, it relates to the fact that Lamont is an observatory in name as well as function. The notion that you collect data and sometimes you don't know where that's going to lead. And that's certainly been true of the Core Lab. Sid, you mentioned momentum. Right now, a lot of the drilling is occurring under the IODP, the Ocean Drilling Program, which is historically related to the deep sea drilling program and so on and so forth. This is one of the longest operating NSF operated facilities that we have in the earth sciences. What's its status now? How's it going forward?
Uh, is that's a sad question to answer. The Joides resolution, I may have already been destroyed, but it's definitely lost. The U.S. does not have a drill ship, um, and the I don't even think that there's a really strong plan underway to fix that problem. And it's broader than just the Joides resolution. There's generally a big problem with the availability of ships going forward. It's really kind of a scary prospect. But IODP has the NSF has committed funding to a new program called SODCO, Scientific Ocean Drilling Coordination Office. Um, and so there's hope that there two things will be happening. One is that we have an absolutely extraordinary archive as a result of the drilling that's happened over the last more than 50 years. And that there is going to be a concerted effort to bring people together in consortia, sort of like as a science team, to use those archive records. And then the other thing is, I hope that the scientific drilling community is going to just keep the pressure on to try to regain our situation in terms of being able to do drilling. There's a Japanese ship and a Chinese ship that are theoretically capable of doing the same sorts of operations, but it's not likely that they're going to be leaving the seas around Asia. So it's definitely a really kind of worrying time in terms of being able to gather more important cores.
And it's not just drilling, it's also the availability of icebreakers and other things as well. So
Yeah.
issues that we're dealing with as well. But let me turn to the Q&A, and there's a question from Professor Rousseau, Dennis Didier. Thank you for being here, about Dansgaard Osher events. But let me first turn to Sid and then go to Brendan on this. But Sid, you remember the work that Gerard Bond did a lot, and also with Wally and so on. A little bit about that history and how that has led to our understanding of essentially ice rafted detritus and its importance.
Yeah, so yeah, that goes back to my postdoc was to come work with Wally and Gerard on the Heinrich events, and that's basically what started both of them being really interested in the ice rafted detritus. My understanding is the story was that Gerard was really excited about grayscale cyclicity, and like everybody else, when you find something interesting, you'd go take it to Wally, and Wally's like, yeah, well, cyclicity, I knew about that, but what are those white layers? And so they sort of dug in, and the reason that they show up as white is because they have abundant detrital carbonate flour in there, and so they really kind of marked the cores. And the first one that they looked at was ODP 609, and they dug in a little bit and realized that those white layers were very rich in ice rafted detritus, and that they correlated to a site that had been published in a marine geology paper in 1988 by a guy named Hartmut Heinrich. And so Wally liked to name things, and he called them the Heinrich events. And they started looking at those, and really close to the same time interval is when the really extraordinary records from Greenland were indicating these very quick cold warm transitions in the Greenland ice core. And so Gerard in 1993 wrote, I think, a really important paper connecting the temperature record from the foraminifera in the North Atlantic to the temperature record from Greenland, and then placing the IRD in the context of that temperature record. So the Heinrich events are sort of a special category of Dansgaard-Oeschger events. They're longer cold intervals within the Greenland ice core records, but they're in the pacing of the general warm cold cycles in the Greenland ice cores and in North American records. But Greenland ice cores are a really spectacular place to sort of see the very strong variations. And there's still interesting, and there's still more to be learned about those. But one of the really big things that I think is an emerging understanding is just how important the extreme seasons between winter and summer are in terms of creating the records that we see from those.
Yeah, thanks. And Brendan, are you seeing any of this in your course as well? Denis Denier is asking that question.
Yeah, that's a great question and something that we're really interested in as well. The the majority of the cores that we collected were very ice proximal, really close to the ice sheet during the last glacial maximum or last ice age, and so therefore those cores weren't able to puncture through that sequence. But we do have a few that go back earlier than that, and some radiocarbon dates that say that we're back older than 30,000 years ago, where we could potentially study these kinds of events. And the postdoc that I mentioned, Joanna Davies, has a record that shows that there is a lot of variability in the paleo environment during that time. And then there's another student working on the project who's been looking at changes in sort of the ice sheet signals during that time. And it does look like there are a lot of changes happening. The real challenge is going to be getting over that barrier of time, like being able to actually get an independent time scale to make a comparison to the Greenland ice core, like was done in the more open North Atlantic, as Sid was just describing a while ago. So I would just say stay tuned. It's an exciting area, and hopefully we'll be able to figure out that sense of time.
It is exciting. And any of you who were around Lamont in the 80s and early 90s remember Gerard Bond's enthusiasm, to put it mildly, about this whole topic. But let's continue with that discussion of dating. And Gary Posen has asked a question regarding to that. But Brendan, a little bit of comparison about the methods. Some of us has always considered paleomagnetics to be obviously cliched magic, as it were, in terms of getting dates out. But relate that to the carbon dating, pardon me, and some of the other work on dating and how that's going forward.
Sure. Yeah. So the Earth's well, okay. One of the best things about the Earth's magnetic field is that it's constantly changing, and it's changing on all kinds of time scales. And so the application of paleomagnetic dating that's most commonly used or understood by the broader community is looking at when the Earth's magnetic field flipped from, so, if we went back 900,000 years ago, all of our compass would point to the South Pole. And because we have a good sense of when those flips occurred, we can use that as a way of telling time, looking for those flips. But the Earth's magnetic field is changing on shorter time scales as well. It changes in its intensity and it changes in its morphology. And so just like probably over the course of your lifetime, you've had to adjust the declination on your compass, that declination is constantly changing through time. And so the work that we're doing on these cores, and I think more broadly, thinking about more recent times, is developing our understanding of how the Earth's magnetic field changes on those short time scales, developing templates for those changes that are independently dated, and then trying to use those templates to constrain the timing of these harder to date areas. And so the example that I showed you there, we were looking at changes in declination and how it changed on timescales of thousands of years. And so theoretically, if you have a really good paleomagnetic signal and a really strong template to compare it to, the resolution that you can achieve in this method is around the timescale that you can get out of radiocarbon dating back when you're in the last glacial interval and earlier. But it's still very much a thing that is that there's a lot of room for development still in the method.
What's the stuff in the cores that is actually producing the magnetic signal?
Yeah, great question. So the magnetic signal is hosted by often by magnetic minerals that form in rocks. Our favorite one is a mineral called magnetite. And so magnetite will erode out of the rocks. Maybe it's because of the glaciers or because of other erosive processes and get transported out to the ocean. And so each one of these particles has a little magnetic moment, and that magnetic moment will align with the ambient field as if it was a compass needle, land on the seafloor. Then maybe there's some mixing and stirring right at the seafloor. But eventually, as the sediments compact, the orientation of those magnetic moments can get locked in with time and record that history of the Earth's magnetic field. And so that's how it would record those directional changes, like those changes in the deformation.
I want to address one of the a comment that Sandy Wissel Brown made about her uncle Albert Crary, who worked in both the Arctic and Antarctic. But turning to Sid, first of all, if you remember Albert Crary, but also Sid, when we look at the obvious differences between the North Pole and the South Pole, the North Pole is the Arctic Ocean, the South Pole is a continent. What does the comparative study of those two polar regions actually tell you? I mean, they are different, but what do they tell you?
Yeah, well, so they are very different, right? We can't have a glacier over the Arctic. But I, you know, I feel like to me it's a little bit like the analogy between studying metamorphic rocks to get ancient tectonics versus looking at the tectonics today. So Antarctica is covered by ice. That's an advantage and a disadvantage, right? Because we can image the ice and we can see what it's doing. If we look at the northern hemisphere, most of the ice outside of Greenland is gone, but there's all these things on the landscape that are the expression of what the ice did on the surface when it was there. So I'm not sure if I'm going in the direction of answering your question, but in terms of studying it, I feel like that's really kind of a good analogy. In terms of sort of the reaction to climate change, Antarctica having been on the South Pole for a very long time, most of the time in the last 500 million years, Antarctica has been on the South, centered around the South Pole. Whereas in the northern hemisphere, it has to be a lot colder in order to build up the ice sheets because they have to build up at a latitude that's a little bit outside of the full polar conditions. Maybe that's getting closer to the question you were asking.
Well, it also might relate to something that Vivian Gornitz is asking, which is what is all of this telling us about the triggers for ice sheet collapse or other large-scale environmental changes?
Okay, well, I'm not sure if I should probably let Brendan answer because I think he's kind of looking at the place where you can see it better. But just in general, I think that the geological evidence and the uh, evidence from looking at modern processes says that ice shelves tend to break up as a result of warming. And so it can be subsurface marine warming, like the fear in the West Antarctic ice sheet is that the circumpolar deep water is coming up and eroding the bottom of the ice shelf, and therefore working towards destabilizing it. Or it can be warming in the summer that actually ends up melting ice that goes down through crevasses, and examples of those kinds of activities are seen today in the modern in Greenland. And so those are the sort of two in member things that are the most likely to work to break up ice shelves and therefore allow the ice streams to move very quickly and calve a lot of ice rafted detritus bearing icebergs into the ocean.
Brendan, you want to add anything to that? Sid pointed to you.
Yeah, I mean that's a great explanation. And I'd also say that, I don't want you to get the impression that the processes that were important for the Baffin Bay ice shelf at the end of the last ice age are the same processes that are important for, say, the Filchner or the Ross ice shelf. They're all different. But by studying these ancient ice shelf systems, we have the ability to see what the range of variability could be. What are the forces that could happen? And make connections between some of the physics that would be the same, or some of the, looking for analogies between, I guess, maybe these competing processes of, say, like ice dynamics versus melting from below versus melting from above, and try to make some connections.
If I
There's been a
could
lot.
say one thing, oh, sorry.
Go ahead, Sid. Yeah.
I was just going to say to kind of bring it back around the opposite direction. And I didn't mention it when the animation happened, but you might have noticed Larsen B ice shelf breaking up in the very early 2000s. That had an absolutely enormous impact on how people thought about what was going on in the Heinrich events in particular, but ice rafted detritus in the North Atlantic, recognizing that like very rapid breakup, and it's basically by internal processes as a result of water kind of just cutting through the ice shelf, and the sort of subsequent speeding up of the ice stream, bringing ice into the ocean. It had a huge influence on how people thought about what had gone on in the northern hemisphere ice sheets.
Okay. And I see Denis Denier just asked, Professor Rousseau just asked another question related to that, which is essentially the correlation of Heinrich events between North and South.
During the time interval of Heinrich events and marine isotope stage 3, I don't know of any evidence from Antarctica for something similar happening in Antarctica. If we go back farther in time, there are events in the older part of the record around Antarctica that I feel like really could be analogous to what happened during the Heinrich events in the northern hemisphere. So from that big region of East Antarctica that's below sea level to grounded below sea level today, it's a fairly distinctive provenance signal, and we have examples of that provenance really being pretty dominant 2 or 3 thousand kilometers away in Pritz Bay. I think those events are probably likely, major armadas of icebergs coming from that region. And then Brendan and I are both a co-author on a paper that came out of our expedition 382, where mostly, we'd see drop stones here and there, but there was this interval where we had layers that were really sort of visibly rich in ice rafted detritus. And Ian Bailey, the other stratigraphic correlator on Expedition 382, was very excited about those as Heinrich events. Whether they were actually Heinrich events or not, they were definitely more like what Heinrich events look like in the North Atlantic than anything else we saw on that expedition. They were about 1.3 million years old.
All right, that's coming along. Um, uh, Michael Emder asked a question that I think is on everybody's minds, which is, what does this mean for sea level rise? And let me just interject that sea level in general and sea level rise in particular are being investigated across the board at Lamont. Everything from the geodynamics associated with isostatic compensation to the ways in which sea level varies currently to the impact of sea level on housing prices in the insurance markets. Even that's occurring. But let me get back to Brendan a little bit. What are your thoughts on where sea level is going?
Yeah, so to preface this, I would definitely defer to a lot of my colleagues here at Lamont that study sea level specifically, especially sea level projections. But what is very clear, I think, from what I've seen from their work, from the IPCC report, from other work you see in the literature, is that these potential sea level pathways are very emission scenario dependent. And so because there are a lot of possibilities of what we'll do in the future in terms of carbon dioxide emission. There could be very high carbon emission scenarios and low carbon emission scenarios. Sea level does seem to be very closely tied to that, to having very moderate to minimal changes over the course of the next century to potentially fairly significant. I know, Sid, you had a figure in your talk.
Yeah, I was just looking at that. For to go to like 50 years in the future, the range of the not non low likelihood high impact storyline is all less than zero point 0.5 meters. And it looks like it ranges from about point 4 to zero point 0.5 meters. Um, of sort of best guess estimate for um, sea level rise based on the projections from the um, emissions and not taking into account the possibility of for some sort of really extraordinary threshold being crossed that leads to these really dynamic ice margin processes that we really just don't have the information to understand well enough.
But that's the issue, really, isn't it? That these projections are based on a lot of assumptions related to basically the emissions load on the atmosphere. There's some recent Lamont papers that have come out on the so-called overshoot problem, which is the notion that even if we stop burning fossil fuels now, we're still going to have temperature overshoots simply because of the inertia in the climate system, the atmospheric ocean interaction, and so on. That's a topic for another of these conversations. But what's missing in all of these, including the IPCC reports, at least in my reading, is this notion of extreme events, essentially, or extreme collapse, and the predictability of that, after all. Are these predictable? Are there things that you're seeing both in the in situ observations and some of the sediment cores in terms of what you might be able to say about the occurrence of these extreme collapses? Anything there, Sid or Brendan?
It, I would say that there are definitely examples in the geologic history of very fast ice retreat. And so this ice retreat that's occurring on the time, by very fast, we're talking geology. So we're talking on the time scale of centuries to maybe even millennia, but of continuous fast ice retreat and lots of discharge. And in the Baffin Bay example that we were talking about, from what we can tell, is that within Baffin Bay, there were a lot of icebergs calving off of the ice margins, starting around maybe like 15,000 years ago or so. And although we don't have an exact constraint on when the larger ice shelf broke up yet, it does seem to have only preceded that event by, say, centuries to definitely less than 1,000 years. And so we know that there are very extreme examples of change. I think we're working really hard to try to figure out what are the timescales associated with those really extreme ice changes.
And the environmental context, right? I mean, yeah.
Yeah,
Yeah.
yeah. By the way, Suzanne McConnell rightly points out in the Q&A that sea level is not this rise is not the same everywhere, and this has to do with everything from geodynamics to uh, the forces from oceanographic currents and so on, forcing things along. Anyway, but it's a combination of physical oceanography, solid Earth geophysics, geochemistry, and all that. That's all underway and important research. Um, let's keep on this notion of the collapse and how we might know more about that. I mean, certainly the work that you're doing, both of you, has to do with understanding the rapidity of change in the past, since Paleo. If you were given let's call it an unlimited budget that would allow you to monitor the ice sheets and the ice shelves, what would you do to essentially give you any evidence that a collapse was imminent? I'd put seismometers on, but I'm a seismologist, so
I think seismometers would be definitely a good thing to add to that. I think having really close observations so you can sort of see where the water's going and the details of how the ice shelf is behaving. Like, is it cracking? What is it looking like in the so the seismology will help with that as well. And then I would argue that still then it it it's it might happen, but if we don't have the context of understanding the magnitude of how things have changed in the past and how they're related to the environmental conditions, then we still are not going to be really poised to predict. We're going to be poised to understand after the fact, but we're not going to be poised to predict. And so one gap that, I find uncomfortable and maybe kind of difficult to fill is between what we can do with the modern observations and what we can do with the geological observations. So many of the geological observations that we're making are, they're very informative, but they're, almost as Brendan alluded to, almost a fundamentally different time scale than what we're needing to know about in order to get to the question of predictability. So if we could get just like the last couple of thousand years at well enough dated and well enough sort of monitored with proxy measurements to fill that gap between modern observations and past observations. I think that would be a really pretty important place to put a lot of effort.
yeah, Brendan, what would you do to try to figure out what's happening in real
I mean,
time?
I like Sid's vision, obviously looking at sort of modern processes, now they translate to the geologic record is really important. And along those lines too, I think that there have been some really exciting projects that have put in ways of monitoring the ocean cavity beneath the ice shelves. There's a lot that we can observe from space, but the ocean cavity beneath the ice shelf is not something that we can. And I think that there's a lot you can learn from continuous monitoring beneath the cavity as well. But the reality is that there is a whole suite of tools that are needed to be able to make these accurate predictions.
I'm going to have one last conversation before we break, but it has to do with the role of ocean currents and their impact on the ice sheets and the ice shelves as well. And Sid, I know you've worked a lot. Uh, Lamont Wally, Arnold Gordon, and others have worked on the so-called ocean conveyor, the role of the circumpolar currents and so on. But Sid, is there anything about current ocean circulation and its changes that might lead to, say, enhanced worries about ice sheet stability?
Yeah, I mean, there's a few. I think the one that sort of kind of the most tangible right now is the fact that in the Antarctic circumpolar region, there's circumpolar deep water is being warmed as a result of global warming, and that warmer water is getting up under the ice shelves. And so I agree with Brendan about the cavity thing because I think that is really a central reason for the fear that the ice shelves are going to be vulnerable to the to global warming is because of not so much the top down warming, but the bottom up melting from the warm circumpolar waters. getting under the Antarctic ice sheet. And then just in terms of kind of driving the whole kind of global climate, there's big unanswered, not perfectly answered at least questions, not uniformly answered questions about what the role of North Atlantic deep water production is going to do in terms of the global climate. And so there, actually the range is almost to opposite extremes in terms of what's going to happen in North Atlantic deep water and what will that do to climate. I feel like there's a lot more that needs to be learned about, how that's going to interact with the climate system.
I think we're going to have to return to this at another one of these observation seminars or webinars, as it were. One last question from Jim Robertson, and maybe to Brendan as head of the core lab these days. What kind of cores are being contributed to the core lab today? And again, the core lab itself, the core repository, I should say, is part of a global network of repositories. But what kind of cores are being collected now?
Yeah. Okay, great question. And yeah, like Art said, so we are one of 4 repositories funded through NSF to archive samples that are collected under NSF programs as well as other programs. There are also 3 repositories that archive all the material that were collected from IODP, the Ocean Drilling Program, and the Deep Sea Drilling Program. And these are critical resources to all of us. And there are so many questions that you can ask with materials that were collected for other reasons, where like these questions weren't even envisioned at the time of collection. And that's especially true for collections like ours that have cores that were collected going back through the 1950s. So today, the cores that are coming in are often more targeted to specific research programs. So like the cores that I was talking to you about that we collected in 2023, in our repository, we had some cores come in that were related to thinking about seismic hazards and geohazards and how that can be used for planning and prediction. We have cores that are coming in for thinking about long-term changes in ocean circulation, and how that affects heat and moisture transport around the planet. Um, yeah, I mean, if there's anyone out there that is looking for a research project, tell them to go check out a core repository because I guarantee you can find something interesting to work on that no one's looked at before.
You heard that. Check out the core repository. Again, one of the most highly visited spots on the Lamont campus. I want to close a little bit with a little bit of an observation here. We celebrated our 75th anniversary last year. We're now in our 76th year. We hope another 75 at least to come. But one of the observations I think a lot of us made last year during the 75th was that despite all that was happening at the federal level in terms of funding, in terms of attacks on the universities, attacks on Columbia in particular, the science never stopped. People were still thinking about what's happening to the planet and how we're going to deal with it, how we're going to observe it, how we're going to analyze it. The theory, the analytical techniques in the laboratory, the observational work that's done in the field, all that continue. And a lot of that would not have been able to continue without the help of our donors and others who are interested in the future of Lamont. So, as we're all looking at our end of the year contributions, I'm certainly doing this myself. We hope that you'll continue to support Lamont. It's important that we have these observation conversations with you. We like doing it. It's fun. It's fun to do. Um, but we are asking you to help us continue our work as well. So to the extent that you feel you can provide that support, please do so. Toward the end of the year, it will help us. We're having a good year in terms of donations, but we're still fighting the good fight at the federal level to ensure that this work can continue. You heard a little bit from Sid about the problems with the ships, obviously. Anyway, let me thank Brendan and Sid especially, and all of you who contributed questions and so on. This has been a fun talk, and we'll be back in February with the next iteration of Earth observations. So take care. Happy New Year. Merry Christmas. Happy Hanukkah. Whatever it is your in your design. We are now adjourned. Take care.
Thank you.
Thank you so much.